part to this conference. So indeed, I would like to talk about a joint work with Grégoire Allaire and some people from the material science department in Grenoble, Rafael Estevez, Alexis, Faure, and Georgios Michailidis. And it's about a work which is about modeling and incorporating some constraints imposed by additive manufacturing technologies into the shape optimization algorithms. So just a very few words as a starter to motivate this study. So as we have seen repeatedly over the week, so shape optimization techniques that have made their way through the industrial community, and they are now well established in this community. But one reproach which is very much addressed to shape optimization techniques is that in general the optimized designs that give rise obtained by this technology, by these algorithms, are in general too complicated to be manufactured by traditional techniques such as milling or molding techniques. So this is one typical optimized design for whatever criterion that is quite representative of something that is obtained by optimized design techniques. So if you give this to engineers, for instance, they will typically tell you that, well, I'm not able to produce this, there are very, very thin bars that are likely to break during the manufacturing process. So this is why there is so great hope for additive manufacturing techniques in industries, that because they are supposed to be able to produce arbitrarily complex shapes. For instance, this is one example of a shape made of metal which has been produced as is in one single piece by an additive manufacturing technique, whatever it is. The problem that, so these are great hopes for these additive manufacturing techniques, but of course there are new challenges, new constraints on their own that they impose on the manufacturing process, and that I'm going to talk about now. So just a very few words about additive manufacturing in general. So as we have seen repeatedly over the week, additive manufacturing techniques, it's actually, or 3D printing, it's more like a common label than one single technique. It's one label for a bunch of techniques which all share in common that they start by a slicing process, meaning the part to be produced is given to a slicer which converts it into a series of 2D slices like this. And so these slices are produced, these 2D slices are produced one on top of the other according to such or such additive manufacturing technology. And all these technologies, they differ from the way to produce each individual slice one on top of the other. So there are several techniques for producing each of these slices, depending on the material to be processed, depending on the cost that we want to spend on this, on the time we want to spend on this, etc., etc. And two very popular paradigms to produce this kind of these slices are first material extrusion methods. So if you have seen probably once a 3D printer in your life, it's likely to be FDM machine tool, which consists on a nozzle that will deposit a molten filament that will follow the contour of 2D slice to be produced. So this is a small picture of it. And so there are also very popular methods, especially in industry, are powder bed fusion methods that are typically used to process metals. And so the technology is quite different in spirit, since now there is a powder bed. And so some metallic powder is spread through the build chamber over here. And then to produce the 2D slice, the ongoing 2D slice, there is a laser that will make the molten powder, the hot powder, that will add several degrees to this hot powder to melt it and to produce the slice that is to be produced. And so here is one small example of a FDM technology, so the technology with the nozzle which is here. And so here is how it processes. So one on top of the other, the slices are built one on top of the other. So it's very much accelerated with respect to the real time process. And so here we pinpoint one of the drawbacks of these technologies that I'm going to talk about, is that these additive manufacturing technologies, for whatever technology, for different reasons, they typically encounter a lot of problems when building overhang features. So overhang features are typically some features like this in shapes. This is a small overhang, this is a large overhang, and overhang is typically a large structure which is hanging over void. And so all additive manufacturing techniques, for different reasons, they experience difficulties when building these kind of features. So in the case of the FDM process that I just showed a movie on, it's fairly clear, because if you want to build this, at some point, since you build one slice atop of the other, at some point you will be building over void, and so the shape will collapse at the point that you build this particular feature here. It's less clear that overhangs are difficult to build for metallic powder processes, because you could say that, well, actually there is a large region hanging over void, but it's not hanging over void, it's hanging over powder, and so the powder could be a support for producing the shape. But the reason is quite different, is that then the molten region, which is here, it will have a high thermal conductivity, so it will typically, the molten material will typically evacuate heat very easily. But if this part sustains about some metallic powder which has very low thermal conductivity, this region will have very much difficulty in evacuating heat, and this could cause warpage. This could cause residual stresses in these regions, which could cause the portion to warp during its cooling. So this is one example of a piece of an overhang feature which should have been completely flat, and just out of residual stresses the piece have warped. So one popular thing that Benjamin has been talking about, among others, to remedy this drawback is to erect a scaffold structure at the same time that the structure is constructed, meaning to build supports so that the shape plus the supports is typically self-supporting, and so there is no overhang region. So this is nice. I mean, for producing some parts, there is no way out of erecting a scaffold structure. But in general, scaffolds are cumbersome because these use more material. These take more time to build at the same time the scaffold and the shape, and the scaffolds, they have to be removed in the end, which is often time-consuming, and sometimes this has to be done by hand, or if there are some internal cavities, it's difficult to remove support. So if possible, for some people, for some mechanical parts where we could afford this, it would be nice to have some shapes, to optimize shapes so that in addition to other constraints, they are self-supporting. This will be one part of the work I will be presenting. Another problem, which is of quite independent nature, which is posed by additive manufacturing technologies, is that in general the material properties, the effective material properties of materials produced by these technologies are not those that are expected and that would be obtained, for instance, if those shapes were produced in one piece by, for instance, molding techniques. So the reason for that is that when the additive manufacturing technologies produce the material by melting selectively some regions, and then the regions cool, and then another region is melted and cooled. So there you have several regions that are melted and cooled together, and some others are melted and cooled apart. And the regions that are melted and cooled together, they tend to create stronger bonds when they cool than regions that are melted apart, which will typically have micro voids, for instance, between such different regions. And so this makes that the effective material properties are anisotropic, and they depend on the construction pattern of each 2D slice in a way that should be modeled and incorporated into the optimized design process. So for instance, here are two construction patterns for a typical 2D slice of a shape. So if you, for instance, this is constructed by FDM, and you see that the nozzle will typically start by making several contours of the shape to be constructed, like this. And then it will fill the infill with some pattern, with rasters of material here, which can have like different spacing out, which can be differently spacing out depending on the constraint that we want to impose. And so here, for instance, the typical shape like this will have like high resistance to traction in the tangential direction to the boundary, and a low resistance to traction in the normal direction to the boundary, because once this layer has been deposited, then it has been cooled, and then when the other one is deposited, there are maybe some micro voids between the different layers that are here. Same, in the infill may be more resistant to traction than in the normal direction to the rasters, which are here. So here is another construction pattern where the nozzle typically would make some concentric pattern starting from the boundary of the layer to the inside of the layer. So there is a need to model this anisotropic behavior and to incorporate it into the optimal design process. Okay, so Now I will be dealing about the mathematical setting that we'll be following before presenting some methods to deal with both constraints related to additive manufacturing. So we are considering structural optimization in possibly simplest form, let's say. So we consider shapes which are like bounded domains, which are clamped on the part gamma d of the boundary, and we apply traction loads F on the part gamma n of the boundary. So this is the setting where we want to use the parts in its final use, and when the engineering will use the mechanical parts. And so under these stresses, under these circumstances, the displacement vector field, it will be given as a solution to the linearized elasticity system that I have given here. So here E is the strain tensor, and A is the Hooke's law that models the material properties of the properties of the constituent material. So so let me say one word about this Hooke's law. So this Hooke's law, it's given when the material is isotropic, meaning that it behaves in the same way in all directions of the space. Then it's read like this, and it depends on two parameters, lambda and mu, the Lamé parameters, which are better expressed in terms of more physical quantities, which are the Young's modulus and the Poisson's ratio. So the Young's modulus is typically the force that you have, the stress that you have to exert to stretch one portion of material from a unit length. So the more, the larger the Young's modulus means the larger the force that you have to pull to stretch one piece of material. So the more resistant will be the material. And the Poisson's ratio is quite independent property, is when you stretch one portion of material from a unit length in one direction, how much is it going to be deformed in the transverse direction in response to this stretching. So this is the quantity that I have written here. So this is a typically material with positive Poisson ratio, meaning that when you stretch one piece of material in one direction, it will just retract in the transverse direction. So this is when the material is isotropic, and when the material is not isotropic, it's anisotropic. It may have different Young's moduli or different Poisson ratio depending on the orientation that you are considering. So in general, the Hooke's tensor is just a general mapping from the set of symmetric matrices to the set of symmetric matrices. And the materials, the type of anisotropy which is most ubiquitous in nature is orthotropy. And it means that we have like D, so meaning 2 in 2D and 3 in 3D, Young's modulus and 3 pairs of Poisson's ratio, depending on what you're considering. And so typical orthotropic material are, for instance, concrete, reinforced concrete, where you have metallic fibers and that's inside a matrix of concrete. And so the material will have like a very high resistance to traction in the direction of the fibers and low resistance to traction in the transverse direction to the fibers. Another type of isotropic material, orthotropic material, is wood, which has typically a strong resistance to traction in the transverse direction here and a very low resistance to traction in the radial direction, which is over here. Okay, so going back to our shape optimization problem, so we will be interested in minimizing some function j of the domain under some constraint, which are modeled by some constraint functional p. So typically the objective function that we want to consider is the structural compliance of the shape, meaning that we want to minimize compliance, we want to make the shape more robust in the context of use, meaning when it is submitted to this context. And as far as constraints are concerned, we'll be imposing like some classical constraints, for instance, volume constraints, but also some new constraints that we want to construct that will enforce the fact if we will cook some constraint functional in such a way that this will drive shapes to be self-supporting, so to be faced, to impose shape, to be overhang free. So this will be one other part of my talk. Okay, so in general, we want to solve this kind of problem, so the optimization problem under constraints. So it's generally good to have a notion of derivative of the functional that we want to minimize. So here we are taking optimization of a set of domains. So we need to give ourselves a notion of differentiation with respect to a domain. And so we rely on Adamar's boundary variation methods, which advocates to consider variations of a shape under the form omega gives omega theta, which is just omega, which is pushed a little bit by a vector field theta. So deformation of a given shape are parameterized by some vector fields. So omega theta is just omega which has been pushed by a vector field theta in all directions of its in all points of its boundary. So when we are given a reference shape omega, we'll say that a function j will be differentiable at omega if the underlying function of the vector field theta is differentiable with respect to this vector field, which makes sense with we have a vector space. So this gives rise to the following expansion around 0, which is classical Taylor expansion involving the shape derivative of the considered functional. So in general, the functional that we want to consider over domains are not so easy, do not depend so easily in such a simple way on the shape, because they depend on the shape via the elastic displacement, which is a solution to a PDE posed on the shape. So it's not an easy dependence on the shape, but there are some quite classical means to calculate shape derivatives, techniques from optimal control theory in general. So I don't want to get back to this. It's not so easy, but it's fairly classical in the literature. The only thing we need to know is that in general, the functional that we will be considering, they have the good taste to have this particular form, meaning the shape derivative given in the deformation direction theta is just the integral over the free boundary, the only one that we want to optimize, of some scalar field, again the normal component of the deformation field, which means that at first order, when the deformation field is purely tangential, then the shape doesn't change at first order, then the functional doesn't change at first order, and the shape derivative should be 0. So this is, for instance, the shape derivative of the compliance that I given before. So in this case, how do we exploit this information when we want to perform or we want to solve typically this optimization program, which is over here? Then this means that if we take theta is minus this field V here, which depends on all the structural optimization problem, it depends on the minimized functional, it depends on the physics at play, then we'll take theta is minus the omega against the normal vector. Then if we plug this inside the defining asymptotic expansion for shape derivatives, this gives us that when we push the shape omega along the direction of this vector field for a small pseudo time t, then at first order the functional that we consider is decreased. So this gives us a rule to say that if we push each part of the shape along this vector field, then we will end up with a new shape which is a little bit better with respect to the minimized criterion. So this gives rise to a fairly simple gradient algorithm for making shape optimization, for instance, which is written here in a very sketch context. So at each we have a series of iterations starting from an initial guess. At each iteration, we calculate the solution U to the linearized elasticity problem. We calculate the adjoint if there is one. Then we calculate the shape gradient according, for instance, to this explicit formula. Then we infer a descent direction by this token over here. And all there is the need to do is now to push the shape omega n in the direction of this small vector field theta n for a small amount of pseudo time to get the new shape omega n plus 1. So this is like a typical gradient algorithm for shape optimization. The way to carry this out numerically is not so simple, so I will use the level set method for shape optimization. So I'm not entering into details here. I have some backup slides if you have some question in the end. It's not easy, but it's fairly classical in the literature, so I will not emphasize on the numerical resolution of this type of algorithm, the numerical implementation. And so let me go back now to how we intend to deal with the overhang features, how we want to construct some constraint functional p omega, which is here, so that if it is satisfied, then the shape should be overhang free. Okay, so first, there is a very naive geometric attempt, which is the first thing that we tried. They say, well, actually an overhang feature is typically by definition a region of the shape where the normal vector n omega is pointing nearly along the vertical negative direction here. So, well, let me cook a functional which just penalizes regions of the boundary where this normal vector is close to the negative vertical direction, say up to a tolerance nu, which is here. For instance, one possibility is to consider a functional like this, an integral over the boundary of the shape of some function of the normal vector, and this function of the normal vector will typically be positive when the normal vector is close to this negative vertical direction, and 0 otherwise, meaning that trying to make this 0 should try to make so that the shape has no region where the normal vector is close to minus the vertical negative direction up to an angle nu. So this is fairly naive, fairly simple, and the good news is that it's very easy to program. You can calculate the shape derivative of this functional, so it's like a typical shape calculus. I'm skipping details, and this is like very cheap to program, very cheap to include inside a typical shape optimization algorithm, as I have shown just before. Unfortunately, this doesn't work. This gives very unsatisfactory reasons. For reasons that Benjamin has already exposed, but I will go back again on this, and which will enlist us to go back to cook another shape functional which goes back to the mechanical origin of overhang features. So let me just give you an example of why, to show you, try to convince you with an example that using this type of functional is very bad for a very good reason. So we consider an example. So here we consider the optimization of a MBB beam, which is clamped here, and we apply like a traction load on the upper part, which is over there, and we minimize the compliance under some volume constraints. So we start from this shape here, and here is the optimized shape that we obtain. So typically the obtained shape, the optimized shape, has very large overhang features on the upper part here, which are very significant for its structural performance, meaning that we apply a load on the upper part here, the shape is clamped on both lower corners, and so to resist the bending which is applied on the upper part of the shape has to put like a lot of material on the upper part. So it's expected that these overhangs will be very difficult to remove because they are very needed for the structural performance of the shape. And so let's see what happens when we incorporate these geometric constraints. Then we end up with this. So this is the optimized shape that results from the calculation. And obviously it's not very good, but actually the algorithm has made exactly what you asked him. I mean, here the constraint functional is almost zero, just because, I mean, instead of removing these large overhangs over here, the optimization algorithm has preferred to make like an oscillatory pattern on the boundary, so that the constraint is almost everywhere satisfied, except as those hanging nodes here, which numerically speaking are almost not seen. Which means that the value of the constraint functional here is very, very small, so the algorithm has made exactly what you asked him to do, but, well, obviously this is not what you want when you want to remove overhangs. So this is why we preferred to develop some other strategy, which could also be used in other contexts, as I will explain now. So we develop another constraint, which is more from a mechanical nature, and which relies on a simplified model for the building process of the shape. So now we are modeling the building process of the shape and not the context of use of the shape that I have presented just before. So in the building process of the shape is included in the build chamber, which is called D here. There is a build table, which is called gamma 0 over here. And so each shape that I will be considering will be included inside this build chamber. And we'll consider all the intermediate shapes associated to the shape omega, meaning the shape omega h, which is omega elevated up to the 8h. So omega h is just omega up to the 8h. So this is this guy over here. And so the boundary of this intermediate shape is decomposed as the part that's laying on the build table, the lateral surface here, and the upper part, which is over there. Okay? In the context of production, so not in the context of use, again in the context of production, the physics at play for each intermediate shape is modeled by another linearized elasticity system, which is different from the one which I have described before, which is used to quantify the mechanical performance of the shape when it's used. Here it's for describing the context of the shape when it's constructed. And so during its construction, the shape is attached on the build table here, and it's only submitted to gravity efforts, which are modeled by the G, the body force G, which is over here. And so we'll measure the mechanical properties of the shape during its construction, of the intermediate shape omega h during its construction, by means of the self-weight, which is just the work of the gravity effects on the shape during its construction in this context of use. And so the constraint that we want to introduce is just a sum of all the intermediates, of all the safe weights of all the intermediate shapes during the construction of the shape. Meaning that if at some point there is a overhang feature, then the self-weight associated to this intermediate shape should be very large, because under gravity effects, the overhang features should be collapsing under the build table. So the intuition is that trying to minimize this should try to make so that there is no overhang feature on any intermediate shape associated to the shape omega. All right? So let me emphasize that we have chosen to model the physical behavior of the shape during its construction by another linearized elasticity system, which is not the one that I used to measure its mechanical performance, but we could have chosen other effects of importance for the shape during its construction. For instance, we could have said that, well, actually the most important effect is not gravity, it's the weight of the nozzle when it's going to pass to create the new layer on the shape, meaning that the intermediate shape could be submitted to a body force which is applied only on the upper part of the intermediate shape. We could have chosen this type of modeling. We could also have chosen to model cooling effects inside the intermediate shapes as the most important physical information during their construction. So this has been done, for instance, by Grégoire and one of his postdoc students, Lucas Jacobsin, to model residual stresses inside the intermediate shapes during their construction. So this type of model of functional here, of constraint functional, could be used to model other effects related to additive manufacturing by exploiting this layer by layer construction process. So now that we have a new shape constraint, you should be able to calculate the shape derivative of this constraint functional. So this is not so easy. So I'm skipping a lot of details here. It's not so easy. The classical technique by using the mapping onto the reference domain and making the differentiation by using the implicit mapping theorem, it doesn't work like this, unfortunately, but it can be done. So I'm skipping details. Then you can calculate the shape derivative of this new functional, which interestingly is the shape derivative at some point is just the sum of all the compliances of all the intermediate shapes which are which are above this particular point. So I'm skipping details, and instead of this I'm just turning to numerical examples. And so here are some examples. So I'm still considering the same example as before. So this MBB beam which is clamped here, and I'm applying a traction load on the upper part over there. And I'm now considering the constraint problem of minimizing the structural compliance of the shape under a volume constraints, and under by adding my new constraint functional, which is aimed at removing overhang features on the shapes. So here is what it gave. So this is the optimized design without any overhang constraints, and these are the optimized designs by strengthening the weight, the threshold for the overhang constraints. So these are the optimized design with a stricter and stricter threshold for this overhang constraint. And so there is a remark, is that it's okay, but it's not very good. So obviously these large overhangs which are in the lower part of the shape, they have completely disappeared. But so you have much less overhangs in this structure here, but still the large overhangs which are on the upper part of the shape, they have not disappeared. And there are two reasons for that. There is one stupid reason and one deep reason why they have not disappeared. So the stupid reason is that first, I'm considering some sum of all the self-weights of all the intermediate shapes, which means that if I have an overhang feature which is in the lower part of the shape, it's going to penalize all the intermediate shapes which are above, so it is going to penalize all the intermediate shapes, meaning that it will be very easy to remove overhang features which are in the lower part of the shape, because they will be very bad for all the intermediate shapes. Okay, so this is why these ones have disappeared and those one have not disappeared. But this could be remedied in a very simple way by putting some weights in the cooking of our mechanical constraints. But there is a deeper reason why these have not disappeared, is that actually our constraint, it doesn't penalize too much completely horizontal features. Because our modeling is just that we consider one shape at each stage of the construction, which means that at some point we will see this feature when we have a completely horizontal region. So this is not too bad with respect to gravity. And on the next day, we will see this guy where all the material has been put at layer H at once, meaning that this is sustained by the lower part here, so this is not too terrible for gravity either. So actually, because we do not model all the intermediate stage where the nodes are going to pass and really to create a overhang here, this is not too terrible with respect to gravity. Well, actually, what we could do is just to replace our mechanical constraint by the mechanical constraint, the version I mentioned, where the weight is applied only on the upper part of the intermediate shape, which is given here. So this is completely fictitious, but it's expected that when you have a very thin completely horizontal region here with a weight which is applied on the upper part, the self-weight will be very terrible for this shape here. So let's verify this. And so here are the shapes that we obtain by strengthening our new mechanical constraint, which is over here. And so in the end, we have a shape that has completely changed, which has some kind of scaffolds here, but which are really needed for its structural performance as well as for its construction. So this is the shape that we obtain. So let's turn now to a 3D example. So we consider the design of a bridge. So the bridge is clamped here, 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 and here. And on the upper part, we have like some uniform some load which is distributed, which mimics, for instance, pedestrians or cars passing over the bridge. And so since we have like a load which is distributed on the upper part, we expect that there will be like a lot of matter over there, and so we'll build the bridge upside down, starting from the top where we expect there will be matter all over there. Okay, so now we minimize the volume of the shape with respect to a constraint on the compliance, and by imposing our new manufacturing constraints. So first, without manufacturing constraints, just minimizing volume under compliance of the under constraint of the compliance, we obtain this. So this is the design, and this is the way the design is constructed, meaning this is the same but upside down. So we see that we have like very, very large overhangs, which are over here, that we expect to remove by using our mechanical constraints. And so this is now what we obtain by using our constraints, by adding our mechanical constraints. So again, this is the optimized shape, and this is the way the shape is produced, meaning the same shape but upside down. And here we see that we have like these walls of matter that make it so that the shape is self-sustaining and overhang-free. Okay, so far for overhang constraints. And so let me turn to the second challenge, let's say, that we want to address with respect to constraints imposed by additive manufacturing processes, which is related to the anisotropy in the effective material properties of the constituent material. So let me remind that the material properties, they are influenced by the path followed by the machine tool during the construction. For instance, here are several paths that could be followed by the machine tool for the construction of one 2D slice of the shape. This would be what would be obtained if the slice were produced by a molding technique, meaning produced at all the material is melted at once and solidifies at once. This is what we would obtain, for instance, if the nozzle, for instance, makes several contours of the produced slice and then fills the bulk by some horizontal pattern. Same thing with a vertical pattern. Same thing but with an isotropic crust by making only one contour of the produced shape, etc., etc. So actually we will only focus on the 2D case, on modeling the effective material properties on the 2D case and on appraising how they depend on the shape itself. And I will try to convince you that modeling what will happen in 3D is no more difficult. The real challenge is modeling what happens in 2D. And our construction, it relies, so we will actually consider two construction plans for a 2D slice that I will mention afterwards. And both constructions, they rely on the notion of sign distance function, so I'll make a very, very short digression about the notion of sign distance function by now. So just to mention that the sign distance function to a given shape omega is just the distance to the boundary with the sign minus when we are inside and plus when you are outside. So these are two circles in 2D, and this is the graph of the sign distance function, which is over here. Okay, so when it comes to the sign distance function, there are several sets that are of interest, and the first set that is of interest is that when we consider a point x in RD, is the set of projection points of x onto the boundary d omega. This is the set of points on the boundary which minimize the distance from x to the boundary. So the skeleton of omega is just a set of points such that where there are at least two projections on the boundary, and on the contrary, when there is only one projection on the boundary, we'll denote it by p d omega, like this. So here is a small example. So we have a shape omega, the boundary is here, and here for the point x prime, which is here, we have two projections that minimize the distance from x prime to the boundary, y1, y2 here. And when we are outside the skeleton, which is this kind of medial axis, then there is only one projection point that minimizes the distance from x to the boundary. So other properties, quite well-known properties of the sign distance function, are that when we consider some shape omega, and when we look at a point which is not on the skeleton, then the sign distance function is differentiable at this point, and the gradient of the sign distance function read like this. In particular, wherever it makes sense, the gradient as unit norm. Now, when the shape is a little bit more regular, then this gradient of the sign distance function is also coincide with the normal vector taken at the projection point. And additionally, if the shape is at least of class C2, well, then it can be seen that d omega is also of class C2 on a small neighborhood, on a tubular neighborhood of the boundary. So for instance, we are here, our shape is here. When we are at a point x, the gradient of the sine distance function is normal to the isolines, which are here, but this coincides also with the normal at the projection point, which is here. And on a small neighborhood of the boundary, which is here, for instance, and actually goes outside the skeleton, then the sine distance function is differentiable, of class C2 actually. So a little bit more properties, and then I will stop with this, is that actually this fact that the sine distance function is differentiable in the neighborhood, in the tubular neighborhood of the boundary when the shape is smooth enough, it allows you to extend the vector field and the tangential vector field, which are only defined on the boundary. This allows you to extend them to a tubular neighborhood of the boundary. By just saying that the normal vector at some point x outside the boundary is the normal vector at the projection point, and same thing for a tangential vector field. Okay? And actually it's possible to calculate shape derivatives for the sine distance function, meaning to calculate the derivative of the sine distance function to a domain with respect to the domain itself in several senses. For instance, for a given point x, you can calculate the sine distance function of x to omega, or you could calculate also the shape derivative of a functional of the form which to omega associates some function, some integral function of the sine distance function. So I'm skipping details, but you can perfectly calculate these shape derivatives and use them in shape optimization algorithm. Okay, so now how do we model our construction plans? So as I mentioned, we will consider two construction plans for each 2D slice of the additive manufacturing process. And the first one is that I've been talking a little bit about, is the so-called cross pattern model, where at first the nozzle, it will make several contours of the produced shape here, and it will then fill the bulk part of the shape with a raster, which can be isotropic or anisotropic with horizontal or vertical rasters, for instance, which could be very well separated from one another, meaning if we want to go fast and not to use a lot of material, or we could be very close from one another also. So there is also a density of the infill part here, which is a user-defined parameter, let's say, depending on the sought application. So how do we model the material properties of these kind of shapes? Then in this case, we'll just make comparisons with what would be the properties of the expected material if the material was produced by molding, meaning melted at once and solidified all at once. Then with respect to these ideal material properties, which are isotropic, when we have to expect that in the crust region, then the material will have like a completely normal, a resistant behavior in traction, meaning high Young's modulus in the tangential direction, but it will have a very low Young's modulus in the normal direction, because this layer here, it solidifies before this one is added, etc., etc. So we have to anticipate this type of anisotropy in the crust region. In the infill region, then both Young's moduli, they will depend on the infill pattern, on the infill density. Meaning if you use like very, very few rasters of material, you have to anticipate that you have very, very small volume fraction in the inside, and so you will have very weak Young's modulus and very weak in both directions. But anyway, you have to expect that the Young's modulus in the direction of the rasters, of the deposition rasters, it will be larger than in the transverse direction to the rasters. So this is the small drawings that are here. So how do we model this from the mathematical point of view? So we have three regions. We have the crust. If we consider that the crust has size epsilon, then the crust will be just the set of points where the sine distance function to omega is smaller than epsilon in terms of modulus. The bulk region will just be this region where the sine distance function is less than minus epsilon, and the void will be the complementary region. And so we'll just compute an effective, we just coin an effective material Hooke's tensor by just gluing three Hooke's tensors, one in the crust, so it will depend on the normal direction to the shape itself, because of what I have said here. One for the void, which will typically be like some small epsilon to avoid degeneracy in the stiffness matrix, and one for the bulk, which will depend on the deposition direction and on the infill density. So this is what I have written here. And so we have another construction plan for each 2D slice, which is the offset model. So this is fairly similar. The nozzle will start by making some contours of the produced 2D slice, but it will go on making these offset contours until the complete inside, meaning until the skeleton of the shape, like this. So in this case, the modeling is pretty much similar, except that in this case, we will just glue together two hook tensors, one for the void and one for the inside, which will depend on the extended normal vector field to the boundary, in the sense that I have just discussed just before. So again, the hook tensor depends on the shape itself because it depends on the normal vector, on the extended normal vector to the shape. All right. So I have promised that it will be no more difficult to consider 3D extensions of this type of hook tensor. Then you have to consider that each slice is produced and then the next slice is produced on top of that. So you just have to expect that the traction properties in the Z direction will be very weak. So it will be the same as the modeling that I've given here, except that you would add like a very low Young's modulus in the Z direction if you wanted to discuss the 3D properties of the produced shapes. And the 2D properties would be the same. They would depend on the shape of the slices. Okay, so this horrible slide is just to convince you that you can calculate the shape derivative of a typical shape functional, which depends on the material properties that depend on the shape itself. They depend on the shape because they depend on the sign distance function to the shape and on the normal vector to the shape. So forget the formula, it's just to convince you that you can do it, it's horrible, that you can do it and you can program it, you can perfectly program it and put them into the shape optimization framework that I presented at the beginning. And so let's turn to some numerical examples now. So we consider a benchmark 2D example, that of the 2D cantilever. So we consider a beam which is clamped on the left-hand side of the boundary and we apply a traction load on the right-hand side of the boundary. And we want to minimize the volume of the shape under a constraint on the compliance, and we start from this initial guess. So here is what we obtain when we just consider like the case of the molded material, meaning the material properties are isotropic and they are the ideal ones. So this is the classical cantilever thing. And this is what we obtain when we consider the offset model that I have discussed before, the optimized shape for the offset model. So we can see at once that the shape is very bad, has very bad performance with respect to the molded case. The material properties are much weaker because we minimize the volume under compliance constraints, meaning that the compliance in any case will be saturated, and you can appraise the performance of the shape just by looking at the volume. And here the volume is very large, meaning that the shape, for giving the same value of the compliance, the shape has to be much thicker. So this is what we obtain when we consider the crust pattern infill, model with either isotropic properties in the crust and the infill but different, or isotropic properties in the crust and anisotropic in the bulk, which are horizontal rasters, anisotropic crust, anisotropic infill, and anisotropic crust, isotropic infill. And what you can see is that actually there is this interesting behavior that when the crust is anisotropic, meaning that it has a strong resistance to traction in the tangential direction, then the cantilever tends to have this rounded shape around the application point of the force, just to withstand the application of the force and to benefit from the fact that it's better to be tangential in this sense because the shape is stiffer in the tangential direction than in the normal direction in this part here. So this is what we obtain for infill density of 0.9, meaning the rasters are very close to one another. And here is what we obtain with a lower infill, meaning that the properties are much worse in the infill than what they were before. And we still observe the shape that tend to inflate because they have like a lower performance, but still we have this interesting property that to withstand the loads, the shape tends to create this rounding to benefit from the tangential resistance to traction, to the better resistance to traction of the crust. Again, with a lower density of the infill pattern, what we obtain. So let's consider one last example, which is very much similar to the one I presented before in this quite different context. So we consider a beam which is clamped here and here, and we apply two loads on the upper part of the shape. Again, we minimize the compliance, the volume under a constraint of the compliance of the shape. And here is what we obtain in the molded situation. So the base case scenario where the shape is, the the constituent material is isotropic and strong in all directions. And here is what we obtain when the crust is anisotropic and the infill is isotropic. Isotropic crust, isotropic infill, isotropic crust, and anisotropic infill. And in the case where the crust is anisotropic, we observe again that we withstand the bending imposed by the two loads which are here. The shape tends to make like a lot of contour on the upper part of the boundary to benefit from the resistance to the tangential resistance, to the better tangential resistance of the shape in this case. And so thank you very much for your attention.
Ask a naive and silly question. Is it possible to have some sacrificial material to avoid the overhang problem?
Yes.
Support you can take.
Yeah, sure. This is a quite different range of applications. So Benjamin has discussed this on Monday, was it? This is a quite different range of applications. And sometimes you don't want, I mean, the industrial study engineers will give you the shape and tell you, this is the shape I want to produce. So now I don't want you to modify the shape or to optimize it, just produce it like this, up to putting some support structure. And then in this case, of course, this is unapplicable. But on some other cases, when you could say, well, I could allow myself to change the shape for the sake of making it self-supporting. So this is a quite different range of applications, but of course, there has been once a paper of Benjamin and Grégoire about optimization of the shape of scaffolds for a given shape to be produced, so that, for instance, the amount of sacrificial material is like least possible, or
questions, comments?
The point. So you said that the powder sometimes can also support a bit.
Sorry?
So you said, or I thought I heard something very interesting that you said the powder can also sometimes
yes.
be a bit. So it's maybe also a nice point to the industry. People who make these machines like that you want some very good conducting powder which is supporting as well.
Yeah, actually, yes. Yes, could be. Yeah, that's right. The overhang feature is a completely different nature in the case. The problem posed by overhangs is of a completely different nature in the case of powder bed fusion technologies. That's right.
Okay. No more? Thanks so much again.